We're now going to proceed to build an initial condition file for our wave simulations. Once again, I'm logged in on the cluster in the home directory. I'm going to now go in the ROMs example directory. I'm going to go in the shallow 2D directory, and then I'm going to go in the MATLAB directory. Okay, so I'm going to run MATLAB in here. I have an alias called MB. Okay, and if I do an ls of sw underscore asterisk dot m, there are two files. The first one is sw create grid, which is what we did in the previous demo. So I'm just going to run this to create the grid. And you can see that this tells me typically some information like the average, the time it takes for gravity waves to cross domain and so forth. And there's another script here, create initial.m, which is used to create the initial condition file. So let's first run this script and create the initial condition file, and then we're going to look into it. So I've run this, and let me just plot now the sea surface height, which is contained in this variable zeta. Okay, I'm going to do pcolor. Well, first I'm going to create a figure. Okay, and I'm going to do pcolor grd.xr comma grd.yr comma zeta. Okay, then actually I'm going to do it. I want to divide this by 1,000 so I have the kilometers. Okay, color map get pmap of, I like this color map here. Okay, so this is our initial condition in the sea surface, which is basically a bump. Okay, and the height of the bump is about 0.5 meters. Okay, so we're going to begin our simulation with a fluid at rest, and we're going to perturb the sea surface by a bump in the middle of the domain, and then we're going to see the adjustment process associated with this, with the propagation of waves away from this bump and so forth. Okay, so this is what we want. Now let's see how we do that. Okay, so the script that I ran in this case, lssw_asterisk.m, okay, is this create initial. Okay, this is, so far we never created an initial condition file manually, so this is the first time. So the first thing I was going to do is I'm going to load the shallow water grid, okay, and which we configure in the previous example, and you know how to configure these grids in the RNT toolbox. Then we're going to give a name to the initial condition file, which again is going to be stored in the input directory. Then we're going to set the time of the initial condition in this structure array called opt. So opt.time equal 1 is going to say that this initial file is going to have one time record, because in principle you could have more, you could create initial condition, or you can create netcdf files like these with more time records. Then we're going to say that the time value for this record is going to be equal to 0, which is 0 seconds in time. And then to create an empty file where we're going to store the initial condition, we can use the function rnc underscore create ini file. And the arguments are grd, which is the grid, and this is useful because it takes all the coordinates and dimensions of the variables. And then the file name, which is what we just stored here, and then opt, which is this optional array. So let's just take these commands here. Let's go back to MATLAB and let's execute these. Okay, so you see that now we've created this file, which is file name. We can do an ls -l. In fact, actually we can do an ncdump of this file, cdump that file pipe more. And in fact, we see now that we have a typical this is initial condition file. If we go further down, we'll find variables like ocean time, which is the time in this case, and then we have u bar, which is the barotropic or 2D velocity field, and v bar. Now, the creation of this file also puts variables like u and v, which are for the for when we run the 3D model, but in this case we will ignore them because we are only running the 2D engine of the model. And so the variables that we really care about are u bar, v bar, and zeta, okay, which is the vertically integrated u momentum, v momentum, and the free surface. Okay, so having said that, then we can go back to our create initial file. And the next thing that we're going to do is we're going to load something called CTL, which is basically a structure array that that has all the information needed to write and read variables from this initial condition file. So we're going to do this file here. We're going to execute this F12. And now if you type CTL, you'll see that this CTL just has a lot of information. It tells you the time records. In this case, there's one record that has value 0. It tells you the file from which this CTL is associated with. And then it has all bunch of information like the month, the year, and in this case, of course, the month is January, year 0, day 0, and the date num, which is the MATLAB format of the date, which is in this case 0 again, because it's year 0. Okay, so with that in mind, then we have the reason why we have the CTL is because we're going to use the CTL to read and write things from files. So the first thing is we're going to now initialize the U bar, V bar, and zeta velocity to be 0. And the dimensions here, for example, for U bar is just going to be grd.l times grd.mp. The dimension of V bar, grd.lp times grd.m. The zeta are grd.lp and grd.mp. Now these dimensions are different because this is in Arakawa grid. So if you remember, you know, the free surface exists on a different grid than the U bar and V bar. Okay, so then we want to make a bump in the sea level. So we're going to say that the amplitude of the bump is about 0.5. It is 0.5 meters. The length scale, you know, of this bump, we're going to make a Gaussian, is going to be about 300 kilometers. So we convert this kilometer to meters. And the free surface is going to be then a Gaussian function with amplitude amp, and then an exponential decay. This is the coordinates of the x direction. So if we subtract delta x here, this means that delta x minus 2, which is the middle of the domain, this is basically centered in the middle of the domain, okay, divided by the length scale square, and centered also in the y direction. So this is just simply a Gaussian. Now if we go further down, there's also another type of initialization that we'll use later, which is the same Gaussian, but now instead of being in the middle of the domain, okay, delta x is going to be actually on the boundary at the end of the domain, on the eastern boundary. So you see here delta x versus delta x divided by 2, which would be the middle of the domain. Okay, so having said that, then we have initialized our variables. So now we just store them using this command called rnt underscore save var. And what this command needs is the CTL, which is this map that contains the information about the file, like the time and so forth. Then you are going to insert ind, which tells basically on which time record you want to store the variable, then the variable name, and then the variable value. So we do this for the various U bar, V bar, and zeta. So with this in mind, really all we need to do then, and this is actually all there is to this script. You know, this is just a plotting function if you want to plot the free surface. Okay, so having said that, then we can execute this command, and you know, it works. When you do this information is saying that it's saving the U bar in file this. The source index, meaning U bar, has just a one time step, and the destination index also has only one. So it's just, you know, writing one time record in the first time record. Okay. So with this, we conclude, you know, this grid, sorry, the initial condition file.